Today we'll be going on with some of the harder topics from vectors, and specifically we'll be going over a very important topic, which is scalar multiplication, or the scalar dot product. It's usually referred to as the scalar dot product because if we have two vectors, u and v, with x and y components, then the scalar product is defined as u dot v. Now, it doesn't matter if you use the dot or the cross, but for vectors, it's very important that you get the notation right, as when you do scalar products like this, you'll be using the dot, not the regular multiplication sign, because that's used in a different kind of product for vectors, which is called the cross product. But specifically, we'll be going over with the scalar or dot product today. And the formula for this, if we have two vectors, u and v, when we do the dot product on them, the way we find this is we multiply the x components and we add them to the multiplied y components. So this is actually relatively simple, but it's important to note that because we're multiplying and then adding the components, the result from a scalar dot product is actually going to be a vector, not a scale, it's actually going to be a scalar, not a vector, is what I should say, which is actually where it gets its name from, which is the scalar product, because it's a way in which we multiply two vectors in order to get a scalar quantity. So this quantity just has a magnitude and it does not have a direction. So this is the formula we'll be using. We just multiply the two x components and the two y components and we add them. And because we're doing multiplication and addition, these are all commutative and associative properties. So it doesn't matter what the order is. So it doesn't matter if you add the y's first, if you multiply the y's first, then add the x's, and it doesn't matter which one you use first, whether it's the u or the v, this will also be equal to v dot u. So the order doesn't matter, is the gist of it. So that's an important thing to know. So you don't have to worry, oh, which one's the first one, which one's the second one. It doesn't really matter. So let's move on to some examples. So this is the normal component form that we've been working with, which uses this 1 by 2. So yeah, this 1 by 2 structure where we line them vertically, not horizontally, which is what we normally do with coordinates. And this is our ij notation. And it doesn't matter what form we represent the vectors in, we're still going to be able to do the same thing with them. So if we want to do the dot product for the first one, we're going to multiply the x components. And so u dot v, we're going to have 7 times minus 1, 7 times minus 1, plus 3 times 6, 3 times 6. And so that's going to give us minus 7, 3 minus 7, plus 3 times 6 is 18. So we're going to get a total of 11. So in this case, our dot product is 11, and it's just 11. There's no direction to that. It's just the magnitude. And for this one, just because it's an ij notation, that doesn't change any of the maths here. We just have to add the right component. We'll multiply the right components and then add them together. And so this is going to be our I components first. So 3 times, and this means 1 because there's nothing in front of it. So that's going to be 3 times 1 plus minus 4. And remember to carry the minus that's on the left of it. So it's going to be minus 4 times 2. And so that's going to give us 3 plus minus 4 times 2, which is minus 8. Minus 8. So it's going to be 3 minus 8, which is minus 5. So for this one, our dot product, now I'll just put this in a different color to show that's the answer. Our dot product is equal to minus 5. So that's it. And it's as simple as that in terms of finding the dot products. But we can actually use the dot products to find some other important quantities. Namely, we can relate the dot product to the angle between two vectors. But before we go into that, if we take the dot product of a vector in itself, it's just going to be the magnitude squared. And that makes sense because essentially what we're going to be doing is multiplying the components and then adding the two components together. So we'd expect to just get the magnitude squared. So this is just a little tidbit that you can use in some given questions later on when we're doing harder proofs using vectors. This might be useful. But we can also, going into what I was talking about, we can also relate the dot product with the angle between the two vectors. So essentially what this equation means, if I have two vectors, u and v, and I want to find the angle between them, theta, then I can use the magnitudes of u and v and the dot product, and I can rearrange this to look something like this. And we can do that to find the angle between them. Now you may be wondering, what are we using to find the dot product then if we've got this formula that gives us the dot product based on this angle? Well, if we know the coordinates of the vectors, then it's not that hard to find the dot product using the previous method. And it's also not that hard to find the magnitudes then, because we can just do the usual formula that we've done previously. So we can find the dot product and the magnitudes relatively easily if we're given the two vectors in terms of position vectors. And then we can use those to find the angle between those two vectors. So that's really helpful. So let's go into an example of how we might go about doing that. Oh, but before that is a formula that basically summarizes what I just said. We can use the fact that we've got this previous formula for finding the dot product, and we can rearrange the dot product using this formula. So looking at the examples now, if we want to first find the dot product, the way we would do that is the same method we were doing. So we multiplied the two components and then add them. So we go 4 times 12 for the x components. So u dot v equals to 4 times 12 plus, and then it's going to be 3 times minus 5, 3 times minus 5, and I'll actually just use a dot for coherency. And then so 4 times 12 is 48, and then 3 times 5 is minus 15, so we're going to have a minus 15. So this becomes 33. So our dot product for this question is 33. Now, if we want to find the angle between the two vectors to the nearest degree, what we're going to want to do is we're going to want to start with our u dot v is equal to u, the magnitude of u times the magnitude of v, times cos theta, where theta is the angle between them. And so we rearrange this to be cos theta is equal to u dot v all over the magnitudes of u times v. So what we're going to be doing from here is we're just going to be finding these quantities. We've already found u dot v, so the dot product between u and v. Now we just need to find the magnitudes, and then we can just rearrange this to find our angle theta, and that's exactly what we want to be doing. So we're going to start with finding the magnitude of u, and we're just going to do that by squaring each component and adding them, and then taking the square root, which is this formula here. So it's going to be x squared plus y squared. So it's essentially Pythagoras' theorem. So we're taking our x component, which is 4. So it's going to be 4 squared plus 3 squared. Now this is actually a very common one. So this comes from the 3, 4, 5 triangle. So if we have a triangle with sides 3 and 4, then the third side is going to be 5. So I actually already know the answer to this one, which is 5, but you can double check that on your calculator. That's a really important one to remember. Not so much because it's hard or particularly important, but just because it comes up a lot, because it's a very nice example. But now finding the magnitude of v, we're going to do the same thing. So now it's going to be 12 squared plus minus 5 squared. So this is going to be the square root of 144 plus 25. And so if we put that into our calculator, we're just going to get 13. So that means if we go back up to this example, we should have u times v. So I'll just clear some room over here and continue the working on this side. So if we want u times v, then what we're going to have is that the magnitude of u times the magnitude of v is equal to 5 times 13, which is equal to 65. And so from here, our cos theta is equal to the dot product, which is 33, which we already learned. So we've got 33 over, and that's going to be 65. So 33 over 65. So we can rearrange this for theta. So we get theta is equal to inverse cos of 33 over 65. And finally, we just put that into our calculator and we find that to the nearest degree, this is approximately 59 degrees. So that means there's about 59 degrees between those two vectors. And then importantly, that isn't with respect to the x-axis, that's just the angle between the two. So what have you learned this lesson? You learned that we can do a scalar or dot product between two vectors where we multiply the two vectors in a way that gives us a scalar, which has no direction. And we can use that to then find the angles between the two vectors using previous formulas. So using this formula up here, which is one that we previously went over. And so that's about it. So you learned about the scalar dot product and how it can be used. I hope that this lesson was helpful, and I hope to see you guys in the next one.